Okay, so maybe at this point, it's a good place to point out the essential distinction between proofs in mathematics and, let's say, the so-called proofs in natural sciences, for instance, in physics. Now, to this date, you shouldn't have heard anything like, for instance, Einstein's theory of relativity was proven. We always hear it as verification. Einstein's theory of relativity was verified in this system, etc. So you can actually, in a mathematical sense, you can never prove a physics theorem. You can only verify it. But in mathematics, our proofs are certain and our proofs are universal. You have your axioms, your definitions, they set the universe, let's say, and when you prove a statement, it's true without any exceptions. Okay, so that's not the case in, let's say, physical or natural sciences. But the foundations of mathematics is extremely important because your proofs are based on those foundations. So in the early 20th century, German mathematician David Hilbert formulated what is called Hilbert's program, because then there was talks about some contradictions in foundations of mathematics. So the results based on them were in question. So this was Hilbert's idea as an effort to come up with a finite, complete set of axioms for the foundations of mathematics, and then you lay out a finite set of axioms, and then you prove that they are consistent. There are no contradictions. So that beyond that point, every mathematician is going to use that set of axioms. And also the idea was show that these are complete, okay? Complete. What does that mean? If you remember the definition of completeness, this means any proposition you can lay out in this given system, you can prove using this set of axioms, okay? But not long after comes into the picture another very brilliant German mathematician, Kurt Gödel. In 1931, he published this paper, and essentially he laid out his famous Incompleteness Theorem. Any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is unfortunately incomplete. Okay? That means there are statements of the language of F which can neither be proved nor disproved in F. So Hilbert's program is scrapped. Okay? It's not possible to come up with a set of finite axioms that is both consistent and also complete. If you want completeness, you will have to deal with contradictions. But if you look for consistency, then you will have undecidable statements. Okay, so a problem that can neither be proven nor disproven in an axiomatic system is called an undecidable problem. And this was a huge revelation, and it sort of gave us the limits of mathematics, so to speak. And we have, in fact, a huge number of undecidable problems now that were proven to be undecidable. What does undecidable mean? It means that in the given axiomatic system, we can never prove them nor disprove them. That means there are certain statements that we will not be able to assign a truth value, either true or false. It cannot be known, okay? I'm going to give you here two famous examples. One is the continuum hypothesis in set theory. We are going to talk about this in either next week or the one next in a couple of weeks. So this is in set theory. And the other one is the halting problem. And this is related to theory of computation. So this is quite related. In mathematics, we talk about undecidable problems for which we cannot give a certain truth value, let's say. And in theory of computation, we have undecidable problems, okay, where essentially we mean by undecidable problem is we cannot actually come up with an algorithm that will produce an answer to that problem.